Hi guys, you're welcome to God Academy. In this lesson, I'll be taking you through magnetic circuit problems, how to solve problems in magnetic circuit. In our previous intro class, I introduced you to all the various terms expected in this particular section. So visit that videos and don't forget to subscribe for any future updates. So for us to solve any magnetic circuit, there are some few things you have to understand. Because we started with the electrical circuit, we need to make some analogies so that everything will be very easier, right? So we have current I in our electrical circuit. When you come to the magnetic circuit side, the current is proportional to what you call flux. Okay, flux, which unit is not Weber. Take note. But that doesn't mean that we still don't have current here. The current in magnetic circuit only function with our magnetomotive force. That is the supply. That one is still current. But ideally, the flow of flux is the current that we know. Okay. The next one is what you call the MMF. I explained magnetomotive force. So here, this is like your voltage difference or your potential difference or what we know in our DC, right? So it's the same as the EMF that you know, right? Nothing changes. And you remember the formula, F is equal to N times I. So a supplied current times the number of turns gives us our total magnetomotive force. Then we have what you call the reluctance, and it's represented as what? This R, right? So reluctance is the same as our resistance. Therefore, by Ohm's law, F is equal to our magnetic flux times what? Our reluctance. Then finally, we have what you call the permeance. Permeance is the opposite of what? Reluctance, the inverse. So we call it permeance. It's also the same as the conductance as we have in electrical circuits, right? Conductance, right? So permeance as this, which is the inverse of this, as simple as possible. Let's solve an example for you to understand this better. A magnetic circuit comprises three parts, series, each of uniform cross section. Take note. They are, so the first part is a length of 80 millimeter and a cross sectional of area 50 millimeter squared. That's the first part. The second part is a length of 60 millimeter and a cross sectional area of 9. Then you have an air gap. I explained that earlier. Air gap of length 0.5 millimeter and cross section. It says a coil of 4,000 turns. We have our 4,000 turns is wound around part B. So it was this part which had a coil of 4,000 turns wound around that. Okay. And the flux density in the air gap is 0.3 Tesla. The flux density in our air gap is 0.3 Tesla. Take note, assuming that all the flux passes through the given circuit and that the relative permeability of a section A and B is what? Mu R is 3000. Take note. So A and B is not an air gap. Air gap means that there is nothing there. So we only use the permeability of free space. But here we are not going to use, we are going to use the relative permeability times our permeability of free space. So we have to estimate the coil current. So this is what we need. The coil current needed to produce such a flux density. So from here, we can say that we are looking for what? Our I. We can find I by knowing F because F is equal to Ni, right? So what are the ways you can do? And here you can list another formula. F is equal to this times what? R. You know that your B, flux density, is equal to what? Your Weber, which is magnetic flux over what? Area. So try and list as many formulas as you know, right? B is equal to mu naught H. B is equal to mu naught mu R H. Once you list this down, then the next thing is getting your parameters. So it has third section. Let's model it. So to model this, our third section will be, we have, let's say, 1, 2, 3, right? Then we have our F, then we have our magnetic flux coming down, right? Coming down. So let's make it an arrow. So we have our first section A, second section B, and third section C. This is our F produced here. So this is where you have the number of turns here, right? Number of turns. So you are looking for the I, and the number of turns N was given as 4,000, right? So you are interested in finding what our I, that is all. To find our I, we simply need to find the total F in the circuit, find the total R in the circuit. We can find I. That is one way. Is that not it? Yeah, to find I, that's one way of it. So let's see what you can do here. Now we'll go back and you see something nice here. But first of all, reluctance, we forgot to write the formula for reluctance. So reluctance is equal to R is equal to L over mu naught mu R A. Please take note of this. This reluctance. That's what I'm saying, that before we can find I, we need to find what F. And to find F, we need to find what R and this. So once we get to find our magnetic flux, our reluctance, we can find the total F, then we can find out our I as easy as what possible. Okay, so let's see. Right now, you come straight to the air gap. The air gap gave us a magnetic flux density, right? So the air gap has a length 0.55 millimeter, then cross section area of 150 mm². So this is what I'll do. So my air gap gave me a B of what? 0.3 Tesla. It has an area of 150 mm², right? That's a length of 5. So let's see. Yes, I'm right. So that's what I have here. So here, remember that the formula I wrote here, B is equal to what? Our flux over area. I can multiply and find my flux. And please, the flux, since they are connected in series, the same flux flows through and return back. It's the same flux. It doesn't change. Okay. So once I find my flux, so you see that flux in air gap is equal to flux in the entire circuit, because it's the same thing that runs through, because they are connected in series. Therefore, B is equal to this, the straight rather, over A. Therefore, I want this to be equal to B times A. This is what I need. Okay. When I get this and I get my R, I can get my F. So once I have this, right, what do I do? 0.3 times my area. Please convert everything to meter squared. So you get 150 times 10 to the power negative 4. Right. Sorry, 1.5 rather, not 150. It's going to be times 10 to the power negative 6. So I'll have 0.3 Tesla times 1.5 times 10 to the power negative 4. And this is going to give me 0.45 times 10 to the power negative 4 Weber. So this is the flux in the entire circuit. Now let's find the respective we want the respective F across each of our 3 systems. The respective F, right? The respective F across each of our system. So I think that we can use our reluctance and our flux to get F, because F is equal to this times what? R. So once I have this, I can find this to find my F, my total F. Because the ultimate formula we want to use is F is equal to I times what? N. N is 4,000, 4,000 tens. So I need to find my total F. So let's find FA. That is the F across A. Remember that FA is equal to this, which is in the total circuit, times my RA, right? So what is the reluctance across my length A? I gave a formula here that reluctance is equal to L over mu naught mu RA, right? So I'll simply write that. So I'll have L times this over, so LA over mu naught mu R times A. As simple as that, right? So we put in our value. So were we given the permeability of free space? So we have the relative permeability to be 3,000, right? 3,000. So we need to multiply that by the permeability of free space, which was supposed to be given. Okay. So it's 4 pi times 10 to the power negative 7. So we have this, which is 0.45 times 10 to the power negative 4 for this, times the length of A, right? What's the length of A? The length of A was given as 80 millimeters. Cross-sectional area 50 millimeters squared, right? 80 millimeters. So I have times 80 millimeters. That's 80 times 10 to the power negative over this. Mu naught is 4 pi times 10 to the power negative 7. And mu r was given as 3000 times our area, which is 50 meters squared. So 10 to the power negative 6 accordingly. Right. That's correct. So this gives us our answer be equal to 19.180 ampere turn. Now we find for FB, which is this times what? RB, right? So what is the reluctance across B? This times LB over mu naught mu R times what? A. Therefore, I'll have 0.45 times 10 to the power negative 4 times my length of B, which was given as what? 60 and cross-sectional area 90. 60 and cross-sectional area 90. 60 times 10 to the power negative 3. All over there. 4 pi times 10 to the power negative 7 times 3000 times it was 90, right? 90 times 10 to the power negative 6. And this gives us our simple answer to be 7.9680. Now we find F of C. This times our reluctance across C, giving us this LC over mu naught. C is an air gap. C is an air gap. It is an air gap. So we don't need the permeability, relative permeability. Only mu naught times what? Times A. So this gives us a simple 0.45 times 10 to the power negative 4 times the length of the air gap, which was 0.5 millimeters, right? And cross section area is 150. So we simply have 0.5 times 10 to the power negative 3. Cross section area is 150. So I'll have 4 pi times 10 to the power negative times 150 times 10 to the power negative 6. And this ends up giving us 119.380. Therefore, my total F is equal to FA plus FB plus FC. And this is going to give me 19.1 plus 7.96 plus 119.3. And all this gives 146.3680. You can make it A, okay? It doesn't change anything. So once you have this, remember F is equal to N times what? I. In the equation, they say that it's 4,000 turns, right? So I have my I to be equal to 146.36 over 4,000. That is equal to 36.59 milliamp. And that is all I have for this problem. Please go over once again if you didn't get it. And don't forget to subscribe, then share.